we can think of one more iteration or one more modification we might make to this experiment that we've been imagining with having a piece of muscle, maybe from a frog or a rabbit, and testing its force production capabilities by zapping it with electricity. In the last video, we talked about doing that at many different lengths of the muscle. So stretch it out a little bit, see how much force it can produce, squish it a little bit, see how much force it can produce. And we saw that there's this optimal length of the muscle, about the resting length of the muscle, that produces the maximum amount of force. So if you go longer than that, or if you go shorter than that, the muscle produces less force. There's one other way that we could think about studying this, which is looking at the muscle's force production capabilities as a function of its velocity. So of course, when you do that experiment that I've been describing and you zap the muscle with electricity, it contracts, right? It pulls itself like this to get shorter, to create force like this. And by doing so, of course, it starts moving. What we could do is we could maybe stretch or squish the muscle out to a certain length. Maybe we squish it down, or let's say let's say we squish it down, and then we start lengthening it or start shortening it more, and we see right when it gets to that optimal fiber length, we're going to activate it fully and see how much force it produces. So we've already done this in the most trivial case of when we do that at a velocity of zero, say meters per second. That's just what happens when you test the muscle's force production capabilities at its optimal fiber length. And usually it maybe produces some amount of force. We'll just call it like 100%. And that's percent of the maximum isometric force of the muscle fiber. You've probably heard the term isometric before. What it literally means, iso is same, metric means measurement. So same measurement means the muscle is not lengthening or shortening. So that's where that term comes from. Isometric exercise, like a wall sit, for example, comes from the fact that muscle fibers are not changing their length when you're doing the exercise. So that's the most trivial case. The velocity is 0 and the force is 100% of the maximum isometric force, because that's how you determine the maximum isometric force. Now, suppose we start shortening the muscle as if it was under contraction. So we allow the muscle to get a little bit shorter, or we allow the muscle to be moving in the direction of getting shorter, and then we zap it with electricity, and we see how much force it produces. And we try that at a bunch of different velocities. Interestingly, you get a curve that kind of looks like this. So very quickly, by the way, the muscle is, even at relatively low velocities, the muscle loses a dramatic amount of its force production capabilities compared to not moving at all. Then, just like with the force length curve, there's this very special point right here called the maximum shortening velocity. And this point is important because if the muscle is moving faster than this, meaning it's contracting faster than this, it produces exactly 0 force. It's totally unable to produce any force at all. So this has important implications for training and rehabilitation, because especially for performance, because in something like a sprint, this is one of the major limits of performance. Now, talking about slow twitch and fast twitch muscles is getting ahead of ourselves a little bit, but it turns out that if the green line is a slow twitch muscle, as you might imagine, as a percentage of its maximum force production capabilities, which of course would be greater in a fast twitch muscle, but as a percentage, even also, fast twitch muscles have a greater maximum shortening velocity. I think it can even be 3-ish times greater. But we'll talk about the differences in muscle types in a later video. What's important to notice about this is, number one, the dramatic decrease in muscle force production capabilities as a function of its shortening velocity. One way of thinking about this, by the way, is that when a muscle is shortening, you're doing what we call a concentric contraction. Something very interesting happens, though, if you try this experiment the other way. So say you lengthen the muscle instead. Now, this would have to come from some external force, of course, because muscles can only contract. They can't stretch themselves out. But if you pull on a muscle, you can make it get longer, even though contraction goes in the opposite direction. So we could express that as having a negative shortening velocity. Something very interesting happens with this experiment if you try to estimate what the muscle force production capabilities are at negative shortening velocities, aka in an eccentric muscle contraction. And that interesting thing is that the muscle can produce more force than its maximum isometric force. I think it goes up to, depending on the muscle and the circumstances, 120 to 180%. So it can be quite substantial, although those benefits flatten out after some particular point. And there's no special name for this point. It's just over here in the negative velocity area. So very important implication here. With eccentric loading, your muscles can produce more force than they can produce at a stop. So this curve is another one of those very important characteristic curves of muscles, and as you might imagine, it also has a name, and it is the force velocity curve. And the force velocity curve has one additional very useful property, which is its relationship to power. And that's what we'll talk about in the next video.